Let's begin class here. This is day 15, so that means we're about halfway done with the semester. Today we'll briefly talk about project number 1. We will continue with factor analysis, and we will also briefly talk about project number 2. Are there any questions before we begin? So with respect to project number 1, obviously everyone, each group had a different data set, so I don't have an answer key to pass out to everyone. So I tried to make a lot of comments on the projects, and hopefully if I did take off points, it made sense why I did that. But of course, if you have any questions about it, let me know. Now, just as a reminder, when you view, so if you turn in a Word document, I'm using the words track changes tool. And it's best to make sure to view my track changes by going to review, make sure all markup is on. You're going to be able to see my tracked comments, changes much better. Now, there are times where an answer is incorrect versus I would have done a problem a different way. And if in both those cases I tried to make a comment about it, obviously if I think it's incorrect, I'm going to take off points. If I think I would have done it a different way, like, I would have chose four principal components rather than 5 principal components, I put that there too. So make sure that you read all my comments, even those that aren't corresponding to something that's incorrect. So were there any questions regarding the project? Okay, let's do a real brief review of factor analysis, and this is going to help us lead up to where we left off from last time. So again, what we're trying to do is find a set of common factors that explain the information that's available in our data. And we like to be able to do that with as small number of common factors as possible. Also, we like to be able to interpret these common factors. And this is something that we're going to spend some time today talking about. And it's both a strength and, I guess, an issue that some people have with factor analysis is the interpretation aspect. As you will see today, there can be actually multiple interpretations of these common factors. So this is what our factor analysis model looks like. We have our standardized variables, we'll call them z's on the left side, and on the right side we basically have a linear combination of the common factors denoted by the f's. We have m total common factors. In this linear combination, the constants are the lambdas. These are parameters that we're going to try to estimate. And then, because we recognize that the common factors will not be able to explain everything that's in the original variables, we have these eta terms, these specific factors at the end of each of these equations. These lambdas also are going to allow us to interpret what these common factors represent in terms of our original variables. So once again, if let's say I have a situation where I have a lambda here that is positive 1, a lambda 2, 1 that's negative 1, and let's say all the other lambdas are 0, then what this says to me is common factor 1 represents a contrast between whatever Z1 represents and whatever Z2 represents. Now, with this model structure, we can also write our correlation matrix in a particular form. And we call this form the factor analysis equations. So notice, for example, 1 is equal to the sum of the lambdas for the first factor, each of these lambdas squared, plus now the specific variance. This is the variance of the specific factor. Also notice here that rho sub Z1 and Z2, in other words, the correlation between Z1 and Z2, is equal to the sum of their corresponding lambdas represented in the first equation and the second equation, the product of those lambdas. Okay, so last time we learned about how we can actually estimate these lambdas. We can use the fact anal function. It gives us maximum likelihood estimates. And last time we left off talking about residuals. These residuals allow us to assess how well the model is doing. Similar to in regression analysis when we had residuals. And based upon these factor analysis equations, this is basically a matrix representation of them. We know these factor analysis equations should be set equal to our correlation matrix. Well, once you do the estimation, it doesn't all work out exactly right. So in the end, we will like these residuals to be as close to 0 as possible. And if they all are, that says the model is doing a good job. If we have some residuals that are kind of far from 0, then that says, okay, this factor analysis model isn't explaining as much about the correlation matrix as we would like. And that questions, is this a good model? So then that leads us then to where we left off. So with respect to the goblet data last time, we found these residuals. And where I have, let's see here, just a little bit of erasing. We found these residuals using matrix algebra, and there was only one residual that maybe caused us a little bit of concern, but in the end, it's not too far from 0. So overall, this seems to be a decent model. Now, if I had a residual of, let's say, 0.4, then that would cause some concern. Because think of it, what it means. And this is the example that I kind of used last time, where if someone told you the correlation between two things was 0.3, and then they came back a few minutes later saying, no, I was wrong, it was actually 0.7, that would cause you some alarm. But if someone instead said the correlation was 0.3, and then said, oops, sorry, I made a mistake, it was 0.4, in the end, in the grand scheme of things, that probably won't make much of a difference to you. And so that's how you can interpret what these residuals represent. Now getting to new material. There are going to be times where we have more variables than in this case with the goblet data, only 5 variables. So it might be nice to have, let's say, maybe a quick way to check all these residuals. Are they larger than what we will like or not? And so what one could do is, I'm not going to go through the details here, but here's the, from last time, here's how we actually use matrix algebra to find these residuals. Let's say I put these into an object called resid2, and then if I say abs for absolute value of resid2, it's going to find the absolute value of all those residuals, one at a time. And then if I say greater than 0.1, it's going to do a logical check. Is the residual, an absolute value, greater than 0.1? And if it is, you get it true. It's not, it's a false. So this is a quick way. Imagine if you had a 10 by 10 or a 20 by 20 matrix. It allows you to see, okay, where is this occurring? And that can be easier than looking at every single number that might be in there. Another thing that you can do then is that if I were to also put the sum function with that, meaning let's add all the trues and falses up. You might be thinking, well, how can you add trues and falses up? Well, R translates the true to a 1, a false to a 0. So notice here, I had a value of 2. Why? Well, because of these two right here. Now remember that the correlation matrix and also the representation for our model is going to be symmetric. So how many of these actual residuals are greater than 0.1? Well, only 1. So just always think of this divided by 2. 2 divided by 2 is 1. Now, you might be thinking, okay, well, if it's 0.1, I have a problem. No, it's just this is a number that I put there because I knew that there was going to be one case where it would come up as true. Maybe, at least 0.2, I start getting worried. If I have, let's say if I use 0.1 there, and I'm having a lot of these residuals coming back to be greater than 0.1 in absolute value, then that would also cause me concern. Also, you could use the call means function to kind of get like an average residual for each of the columns, and that can be helpful as well. You know, especially when you have more variables. Okay. So now a new topic with factor analysis. So how do we choose the number of common factors? Should I use 1? Should I use 2? Should I use 3? And in the goblet example, I said, okay, we're going to use 2 here, but you're going to find out a little bit later on, 2 seems to be okay. And we'll look at that specifically very shortly. And so when you decide, let's say, how many common factors to use finally in the end, there's 2 things to think about. First of all, as you will see shortly, because we're using maximum likelihood estimation, there are some tools available to us to help make that decision. It allows us to say, okay, is 1 better than 2? Is 2 better than 3? And so on. But also something else to think about is this. Do not include trivial common factors. Well, what does that mean? Let me go back to my model here. Let's say for common factor 1, lambda 1 was 1, lambda 2 was 0, and all the other lambdas was 0 as well. F1 would be a trivial common factor. What that means is, okay, all it is just representing Z1. So why don't you just take Z1 out of your factor analysis, just treat that separately, and then do the factor analysis on the rest of the variables. That would be a better way to do it. What this is saying is that Z1 represents something that's distinct among all the, in terms of all your variables. So just treat it separately. So we want to avoid these trivial common factors. Okay. So one commonly used tool when one has a likelihood function, uses maximum likelihood estimation, and one wants to make decisions about a model. One commonly used tool across a variety of different applications, not just factor analysis, is something called a likelihood ratio test. And so in my additional maximum likelihood estimation notes, I have a brief introduction to likelihood ratio tests. I wouldn't be surprised that some of you have seen it before, while others have not. And so just to review this little section here, what we talked about already, we were looking at a specific example dealing with field goal kicking, where we're wanting to estimate the probability of success. And so we were able to use a Bernoulli probability distribution for that. Our random variable is y for success or failure, 1 or 0. And we were able to write out then our likelihood function as pi raised to the sum of the y's, which would be the number of successes, times 1 minus pi raised to the n minus sum of the y's, in other words, number of failures, power. This was our likelihood function. We used this to find maximum likelihood estimates. The way that we did that was we looked at this function as a function of pi. The value of pi that made this likelihood function as big as possible represents the most plausible value for pi. That's our maximum likelihood estimate. And when we had 4 successes out of 10 trials, it ended up being pi was 0.4, or we call it pi hat now. It's equal to 0.4. Okay. Now, likelihood ratio tests. So we're going to form a statistic. You know, in order to do a hypothesis test, you need some kind of statistic. We're going to call this statistic uppercase letter delta. Outside of this class, you typically see people use an uppercase lambda to represent the statistic. Obviously, lambda in this section means something else. It's the factor loading matrix. So that's why I just decided to use a delta instead. And this is what delta looks like. Again, it's a statistic. And since I call it a likelihood ratio test, as you might expect, it's a ratio of two likelihood functions. In the numerator, we have the maximum possible value of our likelihood function when our parameters for whatever probability distribution we're working with, or you can think of equivalent in terms of the model, when the parameters satisfy our null hypothesis, what is the maximum possible value that this likelihood function can take on? That's the numerator. The denominator is a little bit more general. It says, what's the maximum possible value that the likelihood function can take on when the parameters either satisfy HO or your alternative hypothesis, HA. And so we can see that what's in the numerator is kind of like a subset of what's in the denominator. Because notice I have HO here, I have HO or HA there. And so it's a ratio. It's always going to be between 0 and 1. Okay? Now, we need to be able to then determine what would be, let's say, an unusual value for delta if the null hypothesis is true. You know, this goes back to your first stat course. You know, like let's say if you did a hypothesis test of, you know, usually the first one that's taught is something like this, where you're testing the population mean, is it equal to some number, we'll call it mu0 or not. And so we assume the null hypothesis is true, and we look to see, well, what would be an unusual value of some kind of, let's say, t-test statistic. So, you know, you probably wrote it out something like this. And the sample size, S is the sample standard deviation, X bar is the sample mean. And what you do is you plot a t-distribution centered at 0. There's the t-distribution. And basically, anything that's out on the tails of the distribution is an unusual value for your test statistic if the null hypothesis is true, because there's very little probability over there. And so then when you have a test statistic calculated on your sample, if it fell like, let's say, right here relative to the x-axis, then you know, hey, this is unusual, let's reject HO. It would be very unlikely for HO to be true and still observe this particular data. Now we want to do something similar with this delta. Now a long time ago when these likelihood ratio tests were first developed, just in general, not necessarily for factor analysis, a particular individual found that if I took -2 natural log of delta, I could use a chi-squared distribution with this delta. So what this is saying is that if the null hypothesis is true, I would expect my values of delta, if I were to go out and take a sample, calculate -2 log delta, go out and take another sample, calculate -2 log delta, and keep on doing it over and over again, assuming the null hypothesis is true. I would expect, let's say, a shape of the histogram to be very similar to a chi-square distribution, essentially. Now, this all works out if you have a large sample. And the reason being is, what stat majors, for example, would learn not until they're a PhD student, is you would actually learn like how you can mathematically prove that in terms of as n goes to infinity, this statistic has a chi-square distribution. Don't worry about that, but that's basically where this comes from. And as long as you don't have a small sample size, this is going to work out fine. Now, with the chi-square distribution, if you remember, there's always a degrees of freedom parameter that controls the shape. The degrees of freedom here ends up being the difference in dimension between the alternative and null hypothesis parameter spaces. What that just basically means is, if the null hypothesis is true, how many parameters do I have left that are allowed to be anything else? Anything. And conversely, if the alternative hypothesis is true, how many parameters do I have that can be any number? Subtract the two, and then you get the degrees of freedom. Now, for us, are, when we actually do this in factor analysis, will actually provide the degrees of freedom for us, and we'll actually do the subtraction. So we don't necessarily need to worry about some of those details. Okay, so let's look at an application. Yeah.
So in this example, can you, I couldn't follow what was the answer of the unusual value for delta when our null hypothesis is true. So can you show it here in this example?
Sure. We'll do it in this example, and if there's more questions, bring it up. And one reason why I like to say it in that way, which was more general than maybe what you've experienced in another course, is that in another course, you're often given like a cookbook, you could say, in terms of, okay, if I'm greater than the 1 minus alpha quantile from a particular distribution, then I know to reject. Otherwise, I don't reject. And that is one way to teach it. But it also doesn't allow you to gain an intuitive feel for why that is the recipe for deciding to reject or don't. And hopefully with some of the stuff I'll say here, that will be helpful. Okay, so let's go back to this field goal kicking example. Let's say simply I want to test, is pi equal to 0.5 or not? Okay, so I need to find, first of all, delta, ratio of two likelihood functions. In the numerator, I assume the null hypothesis is true and find the maximum possible value that likelihood function can take on. Well, again, let's go back to what the likelihood function looks like. This likelihood function is here. Now notice there's only one parameter in that likelihood function. So if pi is 0.5, I put that in there. I put in my data values. Let's say, again, I observed 4 successes, 10 trials. And that's just what the likelihood function is. It can't be anything else. So the maximum possible value of the likelihood function in this particular case is simply put 0.5 in there for pi, put some of the y's of 4, put n 10, and that's what the maximum possible value of that likelihood function can be, which ends up being 0.0009766. So that's my numerator. Now in the denominator, I need to find the maximum possible value of the likelihood function when parameters satisfy HO or HA. HO is pi is equal to 0.5. HA, pi does not equal 0.5. So the range of possible values of pi, 0 to 1. Okay. Well, what is that maximum possible value of the likelihood function? We've already found it, because that's when we were finding the maximum likelihood estimator. So that maximum likelihood estimator was 0.4. You simply stick that into your likelihood function, and you get 0.001194. This corresponds to that table of different values of likelihood function that we found before. So now if I take the ratio, I get 0.8179. Okay. Now, before we do this next stuff, I'm going to jump ahead here. I have 2 questions for you. Just in general here, not necessarily for the field goal kicking example. Suppose my ratio, suppose this ratio here is close to 1. What do you think that says about the null hypothesis? I think I heard someone say it's true. Is that right? It's kind of saying that, yeah.
All of the possible times that we estimate maximum likelihood it satisfies HO is equal.
I think maybe we should say it this way. It's reasonable to have our null hypothesis. Yeah, essentially, yeah. That our null hypothesis is reasonable given this observed data. Because if I take away that having only that HO restriction, my likelihood function isn't that much higher. And remember what a likelihood function is measuring. is the plausibility of particular values of your parameters. And so if the numerator is close to the denominator, I'm going to have a delta value that is close to 1, suggesting what's happening under HO is reasonable for a particular problem. Okay? So what happens then when I take -2 natural log of delta, though? So I make this little transformation. Well, let's just take a look at some possible values. So let's say -2 log, is this big enough? -2 log of 0.9. So 0.9 is kind of close to 1. Oops. Okay, use the right syntax. You get a value of 0.21. Okay. Well, let's say it's 0.99. You get 0.02. And I keep on getting closer and closer to 0. So the closer that -2 log delta is to 0, the more evidence there is that, yeah, what's happening under HO is reasonable. Now let's look at it from the alternative point of view. Let's say this ratio is close to 0. What does that say about the null hypothesis? No, it's likely false. Again, think about what a likelihood function measures. It measures how plausible your parameter values are. And if you don't have that HO restriction anymore, and that denominator then is much, much higher than what's in the numerator, that says then that restriction of HO is just not reasonable, it's not plausible, given your data. And so delta will be close to 0 when the null hypothesis is false. What does that mean then for our transformation? Well, let's look at 0.1 there for delta. Okay, we get a value of 4.6. Suppose I put 0.01 in there for delta, and you can see that as delta goes to 0, -2 log delta increases. Okay, so when should you reject HO? For a small value of -2 log, when should you reject HO? For a small value of -2 times log of delta, or for a large value? For a large value. And then you might be thinking, well, how large is large? That's where this chi-square distribution comes in. So, actually, I did a little bit of a quick little plot here. So here's a plot of a chi-square distribution with 1 degree of freedom, which happens to be the number of degrees of freedom we have for our field goal kicking problem. The reason being is because in the null hypothesis, if pi is 0.5, we have no more parameters. In the alternative hypothesis, pi is not constricted, and so we have 1 parameter. So if I take 1 minus 0, we get 1. To put it more precisely, it's the difference in dimension of the alternative hypothesis space versus the null hypothesis space. That's the formal way that I put it right up here. Okay, so it's just the difference in the two possibilities for the number of parameters you have available to you under HO and HA. So this is an actual 2-scale plot of a chi-square 1 distribution. We can see it's really a right-skewed distribution. And similar to what I was showing you before relative to the t distribution when we did a hypothesis test for mu, we're looking for unusual possible values of, relative to the x-axis. Where do I have little probability underneath the curve? And we can see that as we get farther and farther out on the x-axis, I have little probability there. And in fact, where I drew this line here, this is the 0.95 quantile from a chi-square distribution. People will often denote this as chi-square, then the subscript 0.95, 1. This value is 3.84. So if I wanted to use, let's say, alpha 0.05 for my hypothesis test as a way to quantify what's unusual and what's not, I would use this as my critical value. And so if I have a negative 2 log delta that's greater than 3.84, I reject. Otherwise, I don't reject. Okay? So in this particular case here, we can see that negative 2 log delta ends up being 0.4. That is less than 3.84, so I would say don't reject HO. Now, just as a little bit of a warning, this doesn't mean HO is true. It just means there's not reason to believe that it's false, given the data. Hopefully, in your very first stat course, your instructor emphasizes we can never prove the null hypothesis to be true in any hypothesis test. So, on a project or a test, if you end up saying HO is true, I will actually take off points for that. Okay. Any questions about this introduction to a likelihood ratio test? Is it intuitive, hopefully? Just a ratio of 2 likelihood functions, and we look to see what are unusual values. So now let's apply this now to factor analysis. Now our hypotheses become much more complicated. The null hypothesis is that we have m common factors. And what that basically means is that you have all these corresponding lambdas. Those are our parameters that we're actually testing. The alternative hypothesis is that more common factors are needed. So instead of m common factors, we need maybe m plus 1 or m plus 2 or so on. And one could derive the negative 2 log delta statistic. You're not responsible for this. As you can see, it's kind of messy in the end. Well, we're working with a much more difficult distribution. But it's the same concept here in terms of how you can think of what this negative 2 log delta is actually measuring. Now, what people who do research in statistics, such as me, what we are often concerned about is, well, how well does this, in this case, a chi-square distribution approximation actually work? And if there's cause for concern, can I get a better approximation? And so what this person by the name of Bartlett did a long time ago, he actually did a little bit of a change to the statistic that ends up being leading to a better approximation for a chi-square distribution. So rather than negative 2 log delta exactly, instead what we end up are going to use as a statistic, for lack of a better letter word, called A. And you can see it looks kind of like the one that we had above, but there's some small modifications to it. Remember, m is the number of common factors, will be under the null hypothesis. P will be the number of original variables that you have. Capital N is your sample size. Of course, like sigma hat is your estimated covariance matrix. And then the stuff that's in the numerator right here represents from your factor analysis model. So we end up using a chi-square distribution approximation with A in the end. There's the corresponding degrees of freedom. As you can see, it's kind of a messy expression for it. So we will apply that shortly. Now, for those of you who come in here with some experience with likelihood methods, you might also know about using what are called information criteria to choose between different models. Basically, the smaller the information criteria value, the better the model is. In particular, the most commonly used one is what's called Keki's information criteria. And so we could actually form this here and say, okay, the factor analysis model relative to the number of common factors that has the smallest AIC represents the best model, the best number of common factors to choose. However, there isn't a good way to implement this in R. I've never been able to find one. If you happen to find one, let me know, because I would like to use that. So for that reason, we will not look at it here. And lastly, we need to talk about something hopefully that you talked about in your first stat course, and that is the difference between practical significance and statistical significance. Again, if we relate it to this hypothesis test of mu is equal to mu 0 versus mu not equal to mu 0, let's say if you reject HO, your instructor might have said, okay, we have a statistically significant result. Maybe like the p-value is really small, so we're going to call that statistically significant. The problem, though, with that is as follows. Let's say, this is an example I often like to use in introductory class. Let's say that I'm interested in doing a hypothesis test such as this, where I'm interested in the mean GPA of all students here on campus. I don't have access to all the student records. That would be like in the registrar's office. Instead, to take a sample, I would need to actually, let's say, ask maybe 100 students, what is your GPA? And based upon that, I do like a t-test to do the hypothesis test. Let's say I reject HO. Okay? I have a statistically significant result. But let's say that I can now, let's say, access all student records, like 25,000 students here on campus. And I find out that the true mean GPA is 2.9999999. Okay. So even though I had a statistically significant result, is this practically significant? No. And that is a problem with hypothesis testing, especially when you have like an equality here. I can typically find a sample size, if I'm allowed to go as high as I want, then I'm going to get in the end get a p-value that's, let's say, less than 0.05. Because it's so hard to be exactly this. And so in the end, what ends up happening with these likelihood ratio tests is that they can actually lead to a situation where it says you need more common factors when, in a practical sense, you don't. Well, how do you judge what's practical then? That's where you look at those residuals. If I, let's say, did a hypothesis test that said, hey, you should have more common factors. But then I look at the residuals, and all the residuals are, let's say, less than 0.05. Then I might be thinking, well, wait a second here. I think this model does an adequate job still. And so even though the hypothesis says you need more common factors, I can go against it. So think of this likelihood ratio test as one tool in your toolbox for deciding how many common factors to use, but don't necessarily say, I have to go exactly by that. Okay, so let's now apply this to the Gallup data. So again, I can use FACT-ANO to estimate the factor analysis model. When I use the print function with the corresponding results, at the very end of the output is where I get the information about the likelihood ratio test. And so, notice R says, test of the hypothesis that two factors are sufficient. That's HO. HA would be more than 2. The chi-square statistic value is 4.74. That is our A. Let me actually write that. So this is our A. 2 factors are sufficient, essentially our HO. P-value 0.0294. So, should I reject or don't reject HO? Well, it depends upon what alpha you use. And what we've, over the last 5 to 10 years in statistics, have tried to emphasize to students is that you got to be careful there about using a strict, let's say, 0.05 cutoff. Because if I use 0.05 as my alpha level, I would reject. It would say more common factors are needed. But if I use alpha 0.01, I would say don't reject the HO. So in these particular situations, it's best to say, well, there's marginal evidence to suggest that more common factors are needed. It's not strong, it's marginal. And that's the way that hypothesis testing was originally, when it was first developed, was meant to be interpreted as. Unfortunately, over the years, people got away with it and they chose strict guidelines. If I had, let's say a p-value of 0.049, hey, that's great, I reject. If I have a p-value of 0.051, oh, then I don't reject. Oh, no, it should be exactly the same interpretation, that you have marginal evidence. Okay. Now, if you want to, you can go inside a mod.fit2. Remember, that's a list type of object in R. And I can extract out statistic. Here is my A. I can also extract out the degrees of freedom, which ends up being 1. And I can also extract out the p-value as well. Okay, so we have marginal evidence just based upon this, that maybe more common factors are needed. Before we look at more common factors, though, how about we look at just one common factor and see what happens? Now, you would expect in this situation, right, the p-value to be smaller, because 2 is kind of marginal, and if I'm only using 1, then you might say, okay, well, if maybe 2 is not working, I doubt 1 would work. And so what would happen if I use 1? So I say factors equal 1. Here's my p-value. It is much smaller. One reason why I want to show you this is take a look at this. Look at the residuals. So I use the same matrix algebra tools as what we saw before to find those residuals. Look how big in absolute value those residuals are. This is a big warning to you that, hey, this factor analysis model with only one common factor is just not sufficient. So this is a good illustration of how those residuals are kind of matching up with what the p-value is representing. Well, what if I use 3 common factors? So I say factors equal 3, and look what I get. Error. 3 factors are too many for 5 variables. This corresponds to some stuff that we were talking about last time, where you can have, let's say, multiple solutions. This is it. And so I can't even use 3. I can use 1, I can use 2. 2 is definitely better than 1. And from a practical context, again, if I go back to my residuals for the 2, in only one case, whereas there was maybe a little bit of concern, but it really wasn't that much. And so based upon this, I'd be satisfied with 2 common factors. I wouldn't really have a problem with using it. So, like for your own, as you will see for project number 2, you're going to need to apply factor analysis to your data that you use for project number 1. And one of the questions will be, how many common factors are needed? And so you're going to need to do some hypothesis tests, look at the residuals to make that judgment. Now you might be wondering, okay, well, where's a good place to start in terms of the number of common factors? And unfortunately, I did skip over that. Where I would start is look at your principal component analysis, how many principal components you chose. Why don't you start with that first as the number of common factors, see how well that does, and adjust accordingly. Okay. So this next set of notes talks about the non-uniqueness of the common factors. This is both a strength and a problem with using factor analysis. This is what's going to allow you to have multiple different interpretations for what your common factors represent. That's why this is called non-uniqueness of the common factors. To help understand why this occurs, we need to introduce what's called an orthogonal matrix. So we've talked about orthogonal vectors before. So if I have, let's say, a vector A, if I take the transpose it times a vector B, and let's say these vectors are orthogonal to one another, what's the end result here? 0. Okay. In a geometric sense, You can think of like how the x-axis on a two-dimensional plot and the y-axis on a two-dimensional plot, how they're perpendicular to one another. That's what basically this idea of orthogonality represents. Now, suppose I form a matrix T of orthogonal vectors as the column. So maybe, for example, here's my matrix, and I'm just going to put A here and B here to represent the first column is an A, the first column is A, the second column is B. Okay? This is going to be like my T matrix. Now, if I were to take T transpose T and multiply it all out, I will get the identity matrix back. Why? Well, the off-diagonal elements will be basically what happens here. The diagonal elements would be like A transpose times A. And something I failed to mention as well, suppose each of these orthogonal vectors have a length of 1. And so if I take A transpose times A, I will get 1. So that's why you get the identity matrix back. Quick little example. Back in the data distributions and correlation section, we looked at this bivariate normal distribution. We found the corresponding eigenvectors for the covariance matrix. So here was one eigenvector. Here was the second eigenvector. And if you were to actually take T transpose times T, you will get the identity matrix back. Try it on your own. Okay, so where does this orthogonal matrix then come into play here for factor analysis? Well, let's take a look at our factor analysis equations. So based upon our factor analysis model, our correlation matrix can be written as lambda, factor loading matrix, times lambda prime plus psi. Remember what psi is? It's a diagonal matrix where I have, let's say, psi 1, psi 2, down to psi p on the diagonal. These are the specific variances, the variances of the specific factor. Now, I'm going to do a little bit of a mathematical trick here. Suppose I put t and t prime right between these two lambdas. This doesn't change anything because t times t prime, or t prime times t, is equal to the identity matrix. The identity matrix times any other matrix is that any other matrix back. So nothing changes. But what I can do is rewrite some stuff now. Suppose I put lambda and t together, and then notice I have a t prime times lambda prime. Well, again, using some matrix algebra results, I can rewrite this as lambda t, that whole thing transposed. And how about we just redefine some stuff? So let's let lambda star now be my lambda t. And so I get back to where I was before, kind of, with my original factor analysis equations. I just have a little star there. And so essentially all I've done is now preserve the equality there, but now I have a new set of factor loadings. That's all. To help see that a little bit better, let's look at this from the perspective of a factor analysis model. For some reason, I decided to put an x tilde there. You could put z there if you really wanted to. So x tilde is equal to lambda times f plus 8. So I've written the model in terms of matrices. Let's put my t prime in there, and that doesn't affect anything. I reorganize some stuff, so I have a lambda t. I have a t prime f now as well. And how about we just say, okay, we'll call that lambda t lambda star. And we'll call t prime times f f star. And now I have this new model. These F stars are a new set of possible common factors. We use the quantities inside a lambda star to now try to interpret it. This interpretation will likely be different from our original lambda, our original F. So, what we see here is that we have non-unique common factors. In fact, there are many, many, many more different of these T matrices that I could use. And I could get different common factors in the end. This, hopefully, maybe is setting off some alarm bells that, okay, so you're saying that I could get different common factors, as many different common factors essentially as I want. Yeah, that's what I'm saying. And if I have different common factors, I have different interpretations of my data. This is the number one problem that people have with factor analysis because of this, the non-uniqueness of these common factors. But this is also what other people say is a strength. Because maybe I could choose my T in such a way that I can come up with an easier interpretation of my common factors. We'll see that as we go along. Now, this idea of choosing a different T is what's often referred to as a rotation. And that's because there can be actually a geometric interpretation of exactly what we're doing here. I show that a little bit later coming up. And the idea here is to try to choose a T such that the values that are inside our lambda stars, which control our interpretation of the new common factors, try to choose those values such that those values are either close to 0, close to 1, or close to -1. Well, why? Let's go back to our original model. So focus on the first common factor. You know, if all my lambdas were 1, -1, or 0, that would really help me interpreting what F1 is in terms of the z's. And so that's why we want to try to choose a T such that that can happen, or get as close as possible to that happening. Because otherwise, if I have, let's say, some lambdas are 0.2, some lambdas are 0.8, some lambdas are -0.2, some are -0.5, it just kind of jumbles up the interpretation. But especially if we can get some that are essentially close to 0. That means, you know, if lambda 2,1 was 0, I'd say, okay, Z2 has nothing to do with F1. That's okay, that makes it a little bit simpler than to interpret what F1 is. That's what we want to try to get. So to give you a brief geometric interpretation of this, let's go back to the goblet data. So here's our factor loading matrix. So this was our original, let's say, lambda hat. We've extracted that before. And let's say let's do a plot of these factor loadings, estimated factor loadings, that is. And so all I'm going to do for my x argument for plot, just take that first column, so that will be corresponding to the first factor. Y-axis is going to be my second column of the factor loading matrix. I'm going to say type equal n. I think we've seen this before, which basically says don't put any plotting points on there. I actually will put some plotting points on there using my text function that we've seen before. Where am I going to plot these like just regular old text? Well, exactly at where the factor loadings are. And I'm going to plot labels corresponding to these row names in my matrix. And so that row.names is a function we have not seen before. code. Let's see here. So here again are those estimated factor loadings. Notice how R has put basically some names associated with each row. Notice you don't see anything above it. So it's not an actual variable in this, it ends up being a matrix. And so the way I can extract it is use a function that's intuitive, row.names, and I get W1, W2, W4, W5, W6. Okay? I'm going to use those as labels then when I do my plot. And this is what I get. So on the x-axis, I have the lambda hats corresponding to factor 1. Y-axis, I have the lambda hats corresponding to factor 2. Now notice where W4, let me actually jump on over here to my notes. Notice where W4 falls. So it has a lambda hat 1, when I would write out the model, that is quite close to 1. Let's actually, just to verify that, we actually did write out the model. Notice how that was close to 0. Notice how this was close to 1. And we see that geometrically on that plot. So it's easy to understand how the common factors are representing how they correspond to W4. It's not as easy for these. Okay. But what if I could somehow, let's say, rotate that X and Y axis? We kind of talked about this before with principal component analysis. Suppose I rotate it in the following ways. So I rotated, that's what's represented in red. And that blue arrow there shows how I'm actually, let's say, rotating the axes there. Now we can see that I have, let's say, a new, let's say, x-axis here, a new y-axis here. Look how close W1 and W2 now are to that axis, meaning it's going to be 0, have a lambda, it will have a, I have to look at it this way, it will have a lambda hat 2 that is close to 0, lambda hat 2 star, let's call it that, that's my rotation, lambda hat 2 star that's close to 0. I'm sorry, I got that wrong. It will have a lambda hat 1 that is close to 0. It will have a lambda hat 2 that is positive in a way. Okay, maybe kind of close to 1. Look at where W6 is. It will have a lambda hat 2 that is about 0, a lambda hat 1 that's going to be positive in some way. Now our factor analysis model is going to be a little bit easier to interpret than what we had before. Is it perfect? No, because we still have that. You know, if we could somehow ideally do a rotation such that, you know, here, let's say those factor loadings, and they all are right there, that would be great. But we don't have that here. But now we're getting a little bit more interpretable model. Okay? So, this is where we want to get. How do we get there? Well, there are multiple ways to do this rotation. Let me also give you a little bit of a side note. There's actually ways that you can figure out what that angle of rotation is. You can say, well, that's a 30-degree rotation. I've taught it before, but in the end, I don't think it's really worthwhile to talk about because you can only see this in 2 dimensions. So if I go to 3 common factors, 4 common factors, 5 common factors, it's going to be hard to see it. And so all the time that's spent trying to figure out this, all the geometry that's involved with it is just not worth it. And so that's why I just leave it more in this intuitive explanation of what's actually happening. So there are multiple ways to figure out how to do this rotation. In other words, to come up with this orthogonal matrix. The most common way is what's called Var-Max. Notice in its name, var, which actually stands for variance, max, which stands for maximum. And you'll see why that's coming up. This is what we're going to use. There are other rotation methods. Here are some packages that give you access to them if you were interested. So let's call this lambda t, lambda times t. Rather than call it lambda star, let's just make it a different letter. It just helps with the notation. Let's call it b, for the lack of a better, a better letter. And so anyway, so what we want to do is find a t matrix such that we get this b matrix. And ideally, so these will be our new factor loadings. And what we just saw is that what makes this easier to work with is when the b's are close to 0, or close to 1, or close to -1. And all we're basically going to do is as follows. Since I have a -1 and I have a +1, how about we think of the b's squared, so that I always have just, -1 squared is 1, 1 squared is 1, okay? So how about we look at the b's squared, and our goal is to find a set of b's that are always close to 0, I'm sorry, set of b squares that are always close to 0 or close to 1. So from an intuitive point of view, what do you essentially want to do with each of these columns of these b's? Again, these columns are how you're interpreting, let's say, common factor 1, common factor 2, and so on. What would you want to do with these b's? You want to maximize their variance. Again, think about, let's say if all the b's were either 0 or 1, versus a setting, let's say the b's were about 0.4, 0.6, 0.5. In which case are you going to have the maximum possible values of your b squares? It's when they're all zeros, when they're all ones. So that's why we want to maximize the variance of a column of b's in terms of the b squares. So what we end up doing is this. We try to find a t that will maximize this expression here. And on the surface, you might be thinking, well, wait a second. That doesn't look like what you just told me about. We were trying to maximize these variances of the b squares. But in fact, it is. So, in your first stat course, you learn about the sample variance expression. Let's say that our data is in the x's. We had a sample variance that looked like this: sum of the xi's minus x bars squared divided by n minus 1. Let's just work with the biased version of this to match up with what actually is going to end up happening for us. One can do a little bit of math and show that this expression could be equivalently expressed like this. The sum of the x's squared minus the sum of the x's, that quantity squared divided by n, and then the whole thing divided by n. It's just using some algebra. Don't worry about it, though. Notice how that expression here looks very similar to this expression that's in parentheses. The difference is that the x's now are b squares. Okay? That's the only difference. The p here, that corresponds to the n that we saw here. P, remember, is the number of the original variables that we have, which means the number of rows that we have for our B matrix. So in other words, what we have here inside the big parentheses is a variance of B's for a column of capital B. Now, we have multiple columns. We have m columns. Remember, m will be the number of common factors. So, how about we just sum over all those columns, these variance expressions, And in the end, we want to find a t that maximizes the sum in the end. Again, remember where t falls or comes about. There are numerical iterative procedures that automatically will find that t for you. Find then the corresponding b's for you. The fact anal function will automatically do it for us. In the end, we don't use this expression in the way that I presented exactly the same. We make a little bit of a change. We divide by the communalities of each of the variables, which just correspond to some common factors, account for more variance of the original z's than others. So just a very small modification. Okay. So we're getting a little bit short on time here, so I'm just going to fill in the blank for you here. So this B represents, again, it's like a factor loading. And so what's going to represent is the correlation between the jth original variable and now the ith new common factor that we have. You know, compare that to what we originally had with the original expression of the model. Okay, let's get into this goblet data. We use the fact anal function just like before, except now for rotation, instead of saying none, we say varimax. What R then gives us is, this is our B matrix. Note that this hypothesis test that we talked about for about 15 minutes ago, those results will always remain the same. So don't worry, think that that's going to change. And so if I were to, let's see here, write out now my factor analysis model using a varimax rotation, this is what I would get. And this is a very common question that I would ask on a test. Now let's interpret this. Notice for common factor 1, so this would be like F1 star, this would be F2 star representing. For common factor 1, we can see that, hey, Z1 and Z2 have a very strong relationship with it. And it has really no relationship with Z6. Z4 and Z5, though, are also related to common factor 1. So let's think about what that means in terms of this goblet. So Z6 is the only thing that's not really playing a role. And so what we can see here is common factor 1 is representing essentially the width of the goblet. Let's look at common factor 2. Strong relationship with Z4. Strong relationship with Z6. Very little with Z1 and Z2. Okay? What are Z1 and Z2? Remember, they represent the top of the goblet. Or, well, Z1 represents the opening of the goblet. And Z2 is the width of the cup. And so the other variables are playing an important role for common factor 2. So we can think of now common factor 2 after this rotation is representing the base of the goblet. And so using similar code as before, I actually did a plot of those common factor loadings. This looks very, very similar to this kind of ad hoc way of me doing the rotation. The big difference, the only difference is this right here. This W6 is actually represented up here. And the reason being is because not only is there a rotation with some of this stuff, there can be what's called a reflection. And basically this W6 has been reflected to the other side. It's not a big deal, but that's why it looks a little bit different. Okay. Now, you might be wondering, okay, what was the T matrix then that did this rotation for us? Well, you can actually extract it from the results of estimating this model. There's a ROT-NOT, rotation matrix component. This is my T matrix. So if I took my original lambda hat matrix when I did not do a rotation times this T matrix, then what I will get is my B. The columns are actually reversed. It's not a big deal there. It's just that's what can happen sometimes, and our with inside a fact anal will actually make the correction. Okay. This is a good place to stop with the notes. Really briefly, I'm going to talk about project number 2. This is due Wednesday, November 1st at 5 p.m. Same format as the previous project. All the groups should be able to use their previous data sets for project number 1. If you have problems conceptualizing how you would use it, I don't think you will, but if you do, just let me know. If you want to use a different data set, that's okay too, but you need to get the data set approved by me first before you use it. This project has 2 components, factor analysis part and a cluster analysis part. The cluster analysis is the next set of notes of what we're going to do after factor analysis. There's not always a good way to assign projects corresponding to the tests. In this particular case, factor analysis is on test number 2, which will be next week. So, what I recommend that you do is that you take a look at project number 2 here and only focus on the factor analysis part for now. You have 5 problems there. This is what I think is important about factor analysis for you to know for the test. Determine the number of common factors to use. We talked about that today. Use the correlation use the residuals in addition to the likelihood ratio test to help make that judgment. Be able to use the Varimax method to come up with a new factor analysis model. Be able to interpret the common factors. This is what we did at the very end. State all the matrices corresponding to that rotation. This part right here is what we're going to do at the beginning of the next class. Similar to how we have principal component scores, we're going to have common factor scores. And it won't be that difficult for us to find them. And that's what we will do. So, once we get to the cluster analysis section, we'll talk about that as well. But I strongly recommend, you don't necessarily need to, let's say, get the factor analysis part done for your project before the test. But it might be good to start playing around with your data, see if you can estimate these factor analysis models with your data, just to make sure that you can do those parts. And if you have problems, let me know, and I'll be happy to sit down with you and talk about it. Okay? Okay. We're just about out of time. So what's next in our class? I'll have my usual office hours after class. On Thursday, we will finish factor analysis. Maybe start cluster analysis. We'll just see how far we get. And we also will review for test number 2. Now you might be thinking, well, wait a second. What do you mean we're already going to review for test number 2? Well, remember, next week is fall break. So we don't have class here on Tuesday. So our next class, Thursday, is the last class before our test, which will be the following Thursday.
So in the test, there is factor analysis and PCA.
Graphics, PCA, FA. Those 3 parts. So looking further ahead again, we have fall break next week. Test number 2 is Thursday, October 19th at 8 a.m. And project number 2 will be due Wednesday, November 1st at 5 p.m. So, any questions? Okay, that is all then here for today.